All right. Good morning, everyone. We're going over Lab 8, Gathering and Understanding Weather Data. Different parameters. Last couple of labs, we were going over some water quality parameters. Now we're looking at water or, water in our atmosphere, so weather parameters instead. So for today's outline in lab, we're going to discuss weather parameters and explore the relationships between these different parameters. And then there's going to be this small video that you're going to watch to explain just to better understand the relationships between some of these, like specifically relative humidity and temperature. We're going to collect weather data using the Weather Underground online application. So it's this website where you're going to be filling out, where you're going to be looking at different sites and also filling out the Canvas doc for that you're going to turn in at the end of lab today. And then we're going to create an Excel graph analyzing USF weather data that was collected around 11 years ago, but it's pretty good data for us to really look at the relationships between these parameters. And then we're going to watch a video experiment, Cloud in a Beaker, to do that. And we're going to end lab with that video. But the objectives today is that we want to measure various weather parameters, including wind direction, which is measured in degrees, wind velocity in meters per second, but sometimes it's given in miles per hour, but it's okay, it's super easy conversion. Miles per hour to meters per second, you can do that online. And air temperature in degrees C, sometimes given to us in degrees Fahrenheit, but those can be, depending on what you're looking at, those can be interchangeable, and just make sure you know which one is which based on the units. And relative humidity recorded in percent, and dew point, which is temperature also recorded in degrees C. We're going to explore the various relationships between these parameters and understand what goes into making a cloud through the a lab walkthrough of what it would look like. So the deliverables for today, at the end of the day, you're going to upload your responses to the Lab 8 datasheet, which is on Canvas, in the Lab 8 Canvas page. And then you're also going to upload an Excel sheet with one Excel graph where we're using the USF data and making a double y-axis chart of temperature and humidity over time. And as a note, there's no lab next week because of the semester check-in. This is basically just a week for you to catch up if you have any late work, or for you to just take a breather before the last final stretch of lab, and then the semester's over in like a couple of weeks actually. So the next meeting we have is the week of April 27th, in 2 weeks. So why should we care about air and weather or climate? There's a lot of different reasons, and these are just a few of them. There is an ozone hole in Antarctica, and it has been increasingly getting bigger over time. And temperature is rising, global warming is definitely happening, and it has a lot of different effects, especially on if we're looking at land ice melting, which is the largest freshwater compartment. If we're thinking about last semester or last lab, when we were talking about fresh water and water that we have access to. So even though this is, the land ice is melting and it's creating more fresh water that we have access to, this also means that there's sea level rise. And sea level rise impacts and compounds with a lot of different things, which could mean more frequent and extreme storms, inland flooding, and erosion in different areas. But another effect of climate as it changes is that there's increased droughts and flooding over time, and that has a lot of different, especially even if you don't live on near the coast, if you live inland, drought or exacerbated wildfires is still a thing, and that could impact you too. And also species extinction, as our climate is changing and as different environments are shifting, sometimes habitats that could only exist in under certain circumstances would change. And so if species don't have their regular or the environment necessary for them to thrive, they could go extinct. So these are a few of the many reasons of why we should care about air, weather, and climate. But now if we're looking specifically at air, what is in the air that we breathe? It's mostly nitrogen and oxygen. So nitrogen, there's around 78% that makes up air. And then we have oxygen too, which makes it up around 21%. But also we have minute traces of water vapor and other gases. So water vapor And things like helium, methane, hydrogen, and all of that, that's also in the air that we breathe. And that it's interesting to think because water vapor has, yeah, a lot of effects on our temperature. So if we're looking specifically at water, H2O can exist in solid, liquid, or gaseous states. The change from liquid to gas is evaporation. From gas to liquid is condensation, and this is usually the two changes that we would see most often. And there is a change from solid to gas, which is sublimation, but it doesn't really happen. Most of the time we see evaporation and condensation. So more specifically, if we're going to talk about evaporation, this occurs where water is plentiful, so over oceans, or other water bodies, or even transpiring vegetation. So on plants, on their leaves, they have spores, and when it gets really warm, the spores open, and the water within the leaves, they evaporate off. There's also, now if we're talking about condensation, this occurs when the relative humidity exceeds 100%. So past saturation. Last lab we were talking, there was like one part where we touched on saturation, where it's like a perfect amount of oxygen, or like the atmosphere or the water in the air, and in or oxygen in the atmosphere and in water, it's at equilibrium. But now if there's more water in our atmosphere, this is when condensation happens, when evaporation is rapid, or where air is cooled. So that's another one. So, but to explain the relationship between relative humidity, dew point, and air temperature, how does temperature change the amount of how humid it is? And what does that mean as our as different places are changing in temperatures? So this video is an in-lab demonstration of what it would look like when, or how much space water would take up as temperatures rise. So let me just play that for you all. And it's just around 5 minutes.
All right, in this demonstration, we're going to demonstrate using these beakers and some water concepts of relative humidity. Now remember, the relative humidity is the amount of water vapor, individual water molecules, in a given parcel of air relative to the number of water molecules that could be in that particular parcel of air. And it turns out that the relative humidity really depends on the temperature. Now it's important to think of air a little bit differently than maybe you usually do. Air consists primarily of nitrogen, 78% nitrogen molecules, another 21% oxygen, that's 99%. The other 1% is just a whole bunch of other stuff we're not going to worry about. But it's also important to remember that those molecules of air are not really interacting with each other. And that means that there's something else in the air too. That means there's space in the air. There's room between those nitrogen and oxygen molecules. And we can put another molecule into that space. And the molecule that we're interested in is water. So think of relative humidity in a sense of how many water molecules we're putting in the spaces between the air molecules, the nitrogen and the oxygen. There's so many spaces in a given volume of air. If they're all filled with water molecules, then we say the air is saturated and the relative humidity is 100%. If there isn't any water molecules in it, then we would say the relative humidity was 0 and all the spaces are empty. But that very, very rarely ever happens in nature. So here I've got 5 beakers. And let's say that these beakers represent a particular volume of air. And let's say the center beaker here represents a volume of air at a particular temperature. And you can see it's about half full of water. If the entire beaker represents all of the space available to put water, it's about half full. So we'd say the relative humidity in this beaker is 50%, because 50% of the spaces have water in it. But what happens as we warm this air up? As air is heated, the molecules begin moving faster. As they move faster, they spread further apart and the volume increases. That basically means we're making more space. And so if we warm it up a little bit, now the air has this volume. It means it's got more space. And the water is not taking up as much of the available space. See, this is not quite half full. The level is lower in that beaker. If we warm it up even more, say to this size, same amount of water vapor, but now we're making even more space, and you can see that it only fills it up a little ways. Certainly doesn't fill it up halfway. But what happens if we go the other way? So, well, when you warm air up, space increases, the relative humidity goes down. Temperature goes up, humidity goes down, unless there's a source of water vapor to put into it. Okay, what happens as we cool this down? Volume is going to decrease, the amount of space is going to decrease, and so now that number of water molecules is taking up more of the volume. Let's cool it down even more. Now we're back where we started at about 50% relative humidity. But what happens if we cool it down even more? Oh, just about full. Now we're almost at 100%. Almost all the spaces are filled with air. What happens if we cool it down even more? And this point where the relative humidity, this temperatures, we're cooling the temperature down. When we reach that point where all the space is gone and the relative humidity is 100%, that temperature is called the dew point. This beaker is completely full. We continue to cool it down, what's it going to do? Yep, it's going to rain. So, when relatively warm air that has a lot of space in it, when it's around a body of water like an ocean, or in the case of where we live here in the state of Tennessee, we get ours primarily from the Gulf of Mexico, that water is going to evaporate into that warm air, taking advantage of all the space that's available. And then as that warm air rises, because it's less dense, begins to expand, begins to cool off. As that air cools, the humidity is going to go up. When it reaches the temperature where the relative humidity is 100%, that's the dew point, then condensation can begin to occur. And if the conditions are right, clouds will form, and as air continues to cool, as the clouds form and thicken, eventually precipitation happens.
Great. So that was just a simple walkthrough of what it would look like as temperature increases in air. What does that mean for relative humidity? And what does that mean as air temperature either gets warmer or it cools down? And what would it look like at dew point? So the dew point is when relative humidity is at 100%, and when it's when the temperature is even lower, then if the and there's like less space or less volume in the air for your water to take up, then your water is going to start to condense, and that's how we get rain. Now, if we're going to go over the relationships between relative humidity, dew point, and temperature, we can first go over their definitions. So relative humidity is the percentage of water vapor that exists in a gaseous mixture of air and water vapor. So if we're referring to that slide or that video from before, just this past slide, if we're thinking about that beaker, so how much water that takes up one of those beaker, what is that percentage of water vapor or water that exists there? And that could be your percentage of relative humidity. The next definition is of dew point, which is the temperature at which a given sample of air will have a relative humidity of 100%. So saturation temperature. Dew point is when your air has that relative humidity of 100%. And in a lab setup, it's very clearly seen, and I'll point that out to you when we see that lab walkthrough later. The relationship between relative humidity depends on air temperature. So when the temperature of air is lower, when it's cooler, then you'll have a higher relative humidity because there's less space in the air for your water to take up. And when it's a higher temperature, when it's warmer air, then there's more space for your water vapor to take up. And then so there's a lower relative humidity because it takes up a lower volume within that air. So the saturation point of air increases with temperature. So as your temperature of your air is warmer, then your saturation point also gets lower. So this makes sense as warmer air can hold more moisture than cool air. So what happens to a glass of cold tea on a hot day? There is this condensation, and as your ice cubes are melting, there's condensation on the outside of the glass and it starts to evaporate out. So that's some like evaporation and condensation that ties into something that we can see in everyday life. So now, more specifically, if we're gonna bounce off of condensation, if we think about the clouds that we see in the sky, they are visible products of condensation within the atmosphere. So, but moisture in the air, they need something to gather themselves around to create these clouds. And what that specific thing that they need to condense around is called a nucleus. And these small particles are called cloud condensation nuclei, and they can come in many forms. So cloud condensation nuclei is what needs to be present for clouds to form. And one version of cloud condensation nuclei is from, or that we can make clouds is through cloud seeding, where we introduce our CCNs to the atmosphere and we force this condensation, we force these clouds to form and eventually produce rain. So this is a form of geoengineering. And if we look at this picture on the side, one way that we can force clouds to appear and make rain is by adding silver iodine or dry ice, mixing that into the air. So already there's moisture, there's gaseous H2O. We introduce our silver iodine or dry ice, and that is our nucleus, which our H2 is going to condense around. And when it condenses around that nucleus, it's going to create liquid H2O, which is going to, this whole process would make our clouds and then produce rain at the end. But CCNs, cloud condensation nuclei, can come in many forms. They are basically just any small particles which cloud droplets can coalesce and condense around. And some of them could be from smoke, either from chimneys, forest fires, all the smoke that rises, volcanic activity, so any ash or sulfate aerosols or any of those small particles, even soil stirred up by wind. If there is like if there's like a lot of construction and if there's like a lot of soil that's stirred up, these are small particles that your moisture can gather around. Sea spray, even sea spray, like the small water vapor, those particles, that small salty water is something that can be a cloud condensation nuclei. And pollen too. So if we're gonna put this into context and look at the size difference of all of these different types of water droplets, we have our typical raindrop, which is 2 millimeters. And if we zoom in, a typical cloud droplet, so the clouds that we see in the air, would be 0.02 millimeters. Large cloud droplets would be 0.05 millimeters. And our cloud condensation nuclei or nucleus is going to be even smaller at 0.0002 millimeters. So these super small particles where our moisture and all of these different like water vapor would condense around is this really small size. And then that would create these bigger, large cloud droplets, typical cloud droplets, or a raindrop at the end when when your clouds are ready to produce rain. So what causes coastal fog in San Francisco? Because fog is a version of clouds in our atmosphere. So if we're now looking at an overview of California, we have San Francisco here, Sacramento, Fresno, and we have our cold California current that's coming down, and that we also have our hot air rising from land in the middle of California, and it mixes with our warm Pacific air. So also sea spray, which is our cloud condensation nuclei, because a few slides ago we talked about how sea spray and those small droplets can act as our CCNs. All of this would produce our fog. So this is a mix of advection and condensation, where warm, moist air from the Pacific, it blows over the cooler air and mixes with our cold California currents. And all of this moisture is going to quickly reach our dew point temperature and condense around our sea spray, our CCN, and create fog. Another water parameter or another weather weather parameter is cardinal directions and degrees. So where is your wind blowing in from? And that can be seen, or like that can be found by looking at this compass, where a typical compass we would have north, which is 0 degrees, east 90 degrees, south is 180, and west is 270. And yeah, this is something that we would look at as one of our weather parameters. So one way for us to measure different weather parameters is through the Kestrel weather meter. And this is a video on how to put it together and how to, and then the next slide is how to use it. So this weather Kestrel meter lab demo, I'm just gonna show it to you all real quick.
Hello, this is a brief introduction to the Kestrel.
It's a little low, but it's like a demo of how to put it together. So I'll just, yeah, the volume is a little low, but you can just watch the video for, yeah.
5500 weather meter. This portable weather meter allows us to take weather readings of parameters that would normally be covered by a weather station that is in place. The parameters covered by this meter include the date, time, the direction, as it is equipped with an internal magnetic compass, wind speed, as well as other functions of wind speed, temperature, wind chill, humidity, the heat index, dew point, the wet bulb temperature, pressure, barometric pressure, altitude, and also provides summary screens of all of that data. In order to function properly in the field, this weather meter is also accompanied by a portable weather vane kit. This kit comes in 5 parts, as seen here, and allows us to build a weather vane. This vane, once assembled, rotates freely around an axis and also holds the weather meter. This can be mounted upon a monopod or a tripod and left in the field to take measurements at an elevation higher than ground level so that we can get accurate readings of wind speed. You can see that it moves freely upon the rotating axis.
Right, so that was just a video showing the different parameters that the Kestrel weather meter can collect and also how to put it all together. The next slide is how it would look like if we were to use it and on USF Hilltop, right in front of the library. This is the field that, you know, where different parameters like wind direction and all of these weather parameters can be taken. And I will also just show this to you now.
Hello everyone. Today we are going to be looking at a field application for the Kestrel 5500 weather meter. Now we understand how to assemble the weather kit and the vane, and now we can see that it is properly put together and placed on a tripod in the middle of an open field. It's important that we have our setup in the middle of an open space so that we avoid as much interference as possible from nearby buildings or large trees. You can see that we are substantial distance from both the nearest building and the nearest tree. This prevents any obstructions and changes that we can see occurring in the wind speed and direction because of our obstacles. Here you can see that as the wind blows, the propeller on our meter spins, and it readjusts itself to face the direction that the wind is coming from. When we are ready to take our readings, we want to make sure that we're about 2 feet or so back from the meter so that we don't interfere with the readings of the wind's velocity or the direction. Each time we want to change the parameter that we are measuring, we will just press the up and down arrows, and then, of course, step back and give it a little bit of time to re-equilibrate itself so that we are making sure we're taking proper measurements. Here we have our Kestrel set to take time and date, wind direction, wind speed in meters per second, temperature in degrees Celsius, relative humidity, and our dew point temperature. We also have options to take pressure readings as well as altitude readings.
So that's what it would look like if we were to use the Kestrel weather meter to collect these different weather parameters. But now there is like a website for us that already has weather meters that collect data for us, and we're going to go to the W Underground website, and we're going to collect some data. You're going to fill in different columns on the chart, and then we're going to go through an Excel walkthrough. So first, I'm going to show you where you can find your doc, the Word doc that you're going to be submitting your answers to. So if we go onto the Canvas page under Lab 8, there is this, there's the intro, background information, pre-lab quiz, and this is the Lab 8 assignment and data sheet, so Word document. And I'm just gonna go through what that looks like when it's done loading. So at the very top, we have our table 1, which we're gonna fill in now, the different weather parameters that we want to look at. So time, wind direction in degrees, wind velocity in meters per second, air temperature in degrees C, relative humidity in percent, dew point temperature in degrees C, and altitude in meters. So we can start collecting this by, let me do a new share so I can have these slides side by side. So we have this, our table, which we want to collect information for, and under lab, like the Canvas page 8, there's also the W Underground link, which is going to take you to this website. And this is the W Underground, just collecting weather of specific places, like specific stations within the place. But we can first go to, under the search bar, we can, under search locations, we can type in San Francisco. And it will give us an overview of the different weather stations in San Francisco. Right now, this is the Forest Knoll station. And when this starts loading, I can show you specifically the different parameters that we will use to fill in our chart. Maybe I'll just make it a little bit bigger. Okay. Okay. Yeah, I'll just make this a little bit bigger. Okay, great. So this is the general layout of different weather stations. If we wanted to pick a different weather station, we can click on webcams, and we can also, under radar and this map view, we can click on Wonder Map to look at the other weather stations in San Francisco. So if we click on Wonder Map, it'll take us to a map overview of San Francisco. And right now it's going to load. We have, we can zoom into San Francisco. Zoom in a little bit more. And on the side, under featured data sensor network, we can click on weather stations. And this very first temperature, wind, that's going to just pop up all of these different stations that collect temperature and wind. And if we zoom in, you can, the point of today is to collect data from 2 different weather stations. So I guess I'll just pick the one closest to USF. So this Inner Richmond station ID is KCASANFR. And if we, if I scroll down a little bit more, if I double click on this and click on the station ID, it'll take us to a layout of all the parameters that we want to collect. So for San Francisco, for this very first column here for the Weather Underground station, we want to collect time. Right now in San Francisco, it's 9:03. And one of the other parameters is wind direction. And wind direction is given to us here in this little compass. So like how we talked about, it's the wind directions in degrees is 0, 90, 180, 270. So right now it's a little bit past 90 degrees. We can say that this is maybe 95, 100 degrees. And that would be this first column here. For wind velocity in meters per second. So where is the wind blowing in from? That can be given, right? Wind velocity here. So the gust is right now, it's a 0.0 kilometers per hour. So there is no wind at all. But if there was a number here and it's in kilometers per hour, you can change this kilometers per hour to meters per second by just copying this entire number and going to Google and just typing in, say, if I was going to go into Google, go into a new slide, I'll paste that number and say 0.0 kilometers per hour to meters per second. And Google will do that conversion for us. And if you just do that, they'll, yeah, you can record that new number down in your column. Next, we have air temperature in degrees C. So air temperature, we can say that if we're looking at this main point, I feel like I need to make this a little bit bigger. This is our main, this big number, 14.0 degrees C, that is our air temperature. If your page isn't in C, in degrees C, degrees Celsius, if you go up in the corner, if you scroll up to the corner of this web page in the top right, there's this settings bar and you might be in Fahrenheit and you can switch from Fahrenheit to degrees Celsius by clicking on and switching between these two. Great. Next, that's how you would find air temperature. Now, if we were to look at relative humidity is given here in this main box in the top. So under humidity, we have 70%, so we can write down 70%. And our dew point temperature, if we also look within the same box, off right around the middle, a little bit to the left, there's dew point, and we have that in 8.6 degrees C. We can fill that in. And our altitude in meters would be found if we scroll up to the top right above the station name. We have elevation, and elevation right now is 63 meters. So we can put in 63 meters. But most of the information that you need for your weather parameters can be found in this main top part in this box and right above here. But now you can go to anywhere else in San Francisco and click on a different station to record this last column with all different parameters. And the whole point of this is because depending on where you are, where your station is, your elevation, are you between two buildings, are you in the middle of an open field, your weather parameters are going to vary. So we're just going to want to compare those two. I'm going to give the next 5 minutes for you all to do that and fill in this last column. If you have any questions on where to find these parameters, you can just unmute yourself. But say if we are going to give 5 minutes, I will check back in on you guys at 9:13.
Maggie,
Yes.
sorry, how did you get to the station summary?
Sure. So if we go back to the main Weather Underground page, you can just type in San Francisco, California. And it's going to give us this very first San Francisco, California is going to give us this random station in the middle of San Francisco. But if we wanted to look at all the stations and pick from that, there's this main map view that once this web page is done loading, we can click on Wonder Map. And in Wonder Map, it'll take us to the map view where we can click on different weather stations.
Okay.
Yeah. And we'll just have to zoom in. And if you don't see the weather stations under sensor network on the side, you can just click on weather stations and this very first option of weather, temperature, and wind.
Okay, thank you.
Yeah, of course, no problem. So on this Word doc, just make sure that whatever station you choose for your second column, that you also just type up the weather station name or ID number in this space here. So did anyone have any questions on how to fill in that second column?
Well, I just had a quick question. For the first column in San Francisco, I just copied down the data you showed us, right?
Yeah, that
Okay.
sounds perfect. You can just do that. Right. So now that if we're going to go over the Word doc a little bit more, we have that first column with the data that I just went over, and the second column where you can just find your own weather underground station within San Francisco to compare to. And if we scroll down for the very first question, for each of these different weather parameters, you're just going to explain why there might be a difference between the weather station near USF and the weather station at your selected location. This maybe a sentence, 2 sentences for each of these. Why would wind direction be different? Wind velocity, air temperature, relative humidity, and dew point temperature. You can talk about how elevation of different weather stations could be different and how, depending on the landscape of where your weather station is, a lot of different factors could be like taken into play, like are there surrounding buildings, are you in the middle of a field, things like that. But that is going to refer to this table 1 that you just filled in. Now, we are going to be looking at USF Environmental Science 100 gathered data, and we're going to be making our Excel graph with our double y-axis. So back in the main lab 8 page, if we were to just go past this wunderground.com link, right underneath it, there's a download Microsoft Excel file containing past weather data from USF. And you're going to click on that and download this data. If you click on this link and it doesn't download, you can click on this black arrow off to the side. And when you open this Microsoft Excel sheet, it's going to look like this. So we have our timestamp. This data was gathered in 2010, and this is like 5 days worth of data where every single second for 5 days, all these different parameters were collected. So from, we have air temperature, relative humidity, barometric pressure, evapotranspiration, year-to-date rain, solar, wind speed, and wind direction. What we're really going to be looking at is these first 3 columns where we're trying to see over time, does air temperature and relative humidity have, can we see the relationship between these 2 parameters over time? So to make our one Excel graph, we are going to select these 3 columns. You can do that by clicking on the letter at the top of the column and then dragging to select column ABC. And now we can, at the top on the toolbar, we can go under the Insert tab right next to the Home tab. We'll click on the Insert tab, and near the middle of this toolbar, there's this XY scatter option, and for one of the charts that we can make. And we were just going to want to select this very first option for scatter plot. So no lines or anything, because there's a lot of data and we wouldn't really need lines to be able to see a clear trend. So we'll just click on this very first scatter option, and it will give us our chart. So I'll just move this over to this yellow box off to the side where it says Insert Graph here. But now we have our chart where air temperature is in blue, relative humidity is in red. This is over 5 days. We have our one vertical axis, but to format this a little bit better, to look at the relationship a little bit better, we can click on the blue line at the bottom and right click, because we want to add in our secondary axis. We're going to right click, and under Format Data Series, all the way at the bottom of these options, if we click on Format Data Series, a window is going to pop up off to the side. And right now we have our primary axis on the left, but we also want to add in our secondary axis on the right. So we'll select secondary axis, and that will change our chart. So we have our secondary axis for air temperature here and our relative humidity on the side here. And now we can see that as temperature goes up, as temperature of air gets warmer, then relative humidity would in turn get lower. And that's kind of exactly what that video was trying to explain. So it makes sense because as air gets warmer, there's more space for water vapor to take up. So then the amount of water vapor in that space is going to go down. So relative humidity is going to go down. And one way to make, now we're just making our chart clearer and just labeling and moving things around to make whoever's watching or like looking at this understand what we're doing. So right now it's not a problem anymore, but the x-axis at the bottom for our dates, it was clustered at the bottom, but we can always change the angles of this x-axis by clicking on it. And when it's selected, the format axis window should pop up, but if it doesn't, you can right click. Once you select it, you can right click. And all the way at the bottom, there's format axis, and this is where you can click and get this window if it's not there for you yet. It's going to first show you axis options, but if you click on this tab where it looks like that square with the 4 arrows in it, this is when we can change the alignment for the dates here. So right now we have middle text direction is horizontal. We can create a custom angle where, let's say we want it to be at 45 degrees. And that'll change our dates to be angled in a certain way, so it's a little bit easier for us to read. Now we know at the bottom this is over time, and this is our relative humidity and air temperature, but we're just going to want to add in our axes titles. And we can do that by selecting our chart. If it's not selected already, selecting our chart. And all the way at the top of the toolbar on the left, under Add Chart Element, we can hover over axes titles, and we can add in our primary horizontal. When that pops up, we can rename this. The title at the bottom is going to be date. So what date, at what point in time are we looking at for our 2 different parameters? And if we go back under Add Chart Element, hover over axes titles, we just added our primary horizontal, but we want to add both the primary vertical and our secondary vertical axis, our title. So we can just select primary vertical first. And when that pops up on our chart, we can rename this to relative humidity. Humidity. And we want to make sure that we have our units in percent. So I'll put those in parentheses. And this is our primary vertical. Now, if we go back under Add Chart Element, hover again over axes titles, we added our primary horizontal, our date, our primary vertical for relative humidity. Now at the bottom of this, all these options, we can add in our secondary vertical. So if we click on secondary vertical, it'll pop up on our chart on the side here on the right. And we can rename this to air temperature. And again, make sure to put in your units. It's in degrees C. And now that we have our axes titles, we can change our main chart title. It doesn't have to be exactly this. You can rename it whatever you want, but just make sure that it's descriptive. So we can say it's relative humidity, which is in percent, and air temperature in degrees C over time. And now I'll just zoom in a little bit more so you guys can see, but this is basically the one graph that you guys need. We have our air temperature at the bottom here, and as air gets warmer, relative humidity would decrease, confirming what we already know about the relationship between the two. Did anybody have any questions about how to do any part of or make any part of this graph? Yes.
Can you go over the dates really quickly?
Sure, like how to
Like the 45 degrees, yeah.
Yeah, so you'll select your dates and you can right click and all of these options would pop up. And at the very bottom of these options is format axis. If we click on format axis, the window off to the side would pop up. And right now it's under axes options, minimum, maximum, and things like that. We can click on the tab right next to it, which is for alignment. So it's this white square with the 4 arrows in it. And under vertical alignment, text direction, custom angle is this third option where we can just put it in. Right now it's 45, I guess we can make it 50. Yeah, or it is 40. And that's how we can put in the custom angle.
Okay, thank you.
Yeah, no problem. Did somebody else have a question? I think I saw someone raise their hand.
Yeah, when I clicked on like the data for the column A, B, and C, it gave me like a weird looking thing.
Sure. Yeah, so I guess make sure that make sure that you don't just click these first 3 and just try to select all of them, because there's a couple of thousands of data points. So I guess just to select them, click on A, B, C, the very top letters of these cells, and that would select all of the data underneath it. And then go into insert, and under this toolbar, click on the XY scatter and choose this very first option. Yeah, and your chart should come out looking like this at first, and then we're gonna adjust it. Was it were the data points just not showing up, or
It just doesn't look the same. Like, I don't know how to explain it. It's kind of like cut out in the middle.
okay, here, let me stop sharing and let you share so I can see what's going on. Okay, I think you're allowed to share now.
How do I screen share it?
So at the bottom, right
Oh,
next.
there, I got it.
Okay, cool. Okay, awesome. Okay. Okay. This is really weird. Okay, let's see. Can you just
have the
delete?
timestamps in the data?
I'm sorry.
I guess because she doesn't have the timestamps in the graph too.
Yeah, can you delete this chart, and then let's try this again. Right. So you selected ABC, and then go under insert, scatter, very first XY scatter. Okay, so why don't we see, can you make your chart a little bit bigger? Okay, so the data off on the end is showing up. I don't know for October 17. Super random numbers. Wait, okay, let me see. Okay, I guess I would try to just, I don't know why on the legend at the bottom, all those numbers are popping up. You can, like, if you can adjust that, if you just click on the legend, I think you can format legend. And just, yeah, I guess clean up the text for that. I would say try just deleting this web file or just like closing this page down and then opening it up again, because I don't know what these random points are. Yeah. Yeah. Try just not saving your work for this and closing down this Excel file and then opening it up again and then try making these graphs. If it's still showing up kind of weird like this, you can stay a little bit after class and I can see if I can just help you one-on-one on how to fix this.
Yeah, because I already re-downloaded it because I thought, oh, I probably just switched something around. But when I did it again, it did the same thing. So I was like, okay.
Yeah. Okay. Yeah. Why don't you just stick a little bit after lab and then I can see if I can like help you through this part. Yeah.
Okay, thank you.
Yeah, of course, no problem. So, okay, actually, let me share the Canvas page and show you all what you need to do. So after you have your Excel file with your one graph, you're going to continue answering the questions in the Lab 8 assignment and data sheet, this Word doc. So if we click into that, table 1 is filled out and question 1 refers to table 1. We have question 2, which describe the conditions. Oh, okay. So that's going to be referring to the lab video at the end. So let me go back to the PowerPoint, and the weather meters and these different weather parameters is what we just collected. But now we're going to be looking at making clouds in a beaker in a lab setting. So, and how does relative humidity change to temperature?
Hi, this is going to be a demonstration walkthrough of the cloud in a beaker portion of the weather lab. So first things first, you can see here that we have our hot plate / stir plate set up. We have a dry 600 milliliter beaker, and we have our magnetic stir bar sitting inside of it already. This guy. So before we turn on the heat, we'll add a couple of drops of water. And we're going to cover our system to make it into a closed system. And this is just using a little bit of aluminum foil. Okay. Go ahead and turn our stir bar on. So it should be spinning at about 600 revolutions per minute. And we'll also turn the heat on to about 100 degrees Celsius. Now, what the stir bar does is it circulates the air, and the heat will eventually evaporate the water and bring water moisture into the air. So conditions inside of our beaker should take about 10 minutes or so to stabilize. And in the meantime, one of the things we're going to want to be aware of is how the conditions inside of this beaker should change. So we won't sit through the whole 10 minutes, but I will pause here and there and bring us back in to take a look at how the conditions have changed over time. And actually, even now we can see the beaker clouding up a little bit, so let's zoom in and see if we can take a look at that. Yeah, where the beaker was clear before, we now see a little bit of cloudiness film forming, and that's the condensation from the water vapor right alongside the inside of the beaker. And one very interesting thing to be aware of is, just get this to focus, is right here. We see a line. The condensation is not formed here, but it is forming right here. It may not be quite as visible on camera, but I can see it quite clearly, and hopefully it'll become a little more distinct as our experiment rolls on.
So now we're just going to speed through maybe around 10 minutes or so. But we can see that at this point, this line, it's easier to see if we're paying attention or if we're looking at these numbers, these dashes on the side of the beaker. This line of condensation that's moving up forward, that's our dew point. Our dew point where relative humidity is at 100%, and it's moving upwards and changing as the few drops of water is heating up and stirred together by the stir bar and heated up by like the hot plate. But our line of condensation is moving.
Okay, so it's been about 10 minutes or so, and the conditions inside of our beaker look like they're about stable, meaning that we don't quite see the condensation line rising very rapidly. As I lower my finger down the side of the beaker, this upper portion is relatively cool to the touch, but as I get lower and lower, there is a lot more heat. It's a lot warmer closer to the bottom of the beaker, and that makes sense as the bottom of the beaker is close to the hot plate. So as far as conditions inside of our beaker go, we see that it is cloudy or is full of condensation near the top, and is clearer, meaning there's a lot less condensation near the bottom. Closer to the top, we have a cooler section, and at the bottom, we have a warmer section. Now, moving on to the next part of our experiment, we're going to go ahead and open up our system to add just about 50 milliliters of water to our beaker. So here, we pour out approximately 50 milliliters, and add that to our setup. Now I'm resealing our beaker, and what I'm going to do is put a little bit of ice on top of it. So just as we saw from the first part of our experiment, we had a temperature gradient, a temperature differential, warmer zone near the bottom and a cool zone near the top. We're going to replicate and actually emphasize that same thing here. And this mostly is for the sake of making it go a little bit faster. So we definitely have that warm spot near the hot plate. And here, with our ice, we force a cooler spot, a much colder spot, in our beaker near the top. Now we're going to give this about 5 or so minutes to stabilize again, and after we do that, we'll go on to the last part of our cloud and beaker experiment.
So adding in ice at the top and along with putting in water is to create this difference where we're just kind of exacerbating and just making this process of condensation in clouds faster. But it's also to sort of mimic what it would look like if we had our water body, our say an ocean, and if we had a cooler zone at the top in our atmosphere, and how would clouds form like that? So this is one example, or this is how we can just force the process to go a little faster and make our clouds a little bit easier.
Alright, so it's been about 5 minutes, and let's take a look at our beaker. Conditions inside should have stabilized. So we see a lot of condensation on the outside, or rather the inside of the walls of our beaker. And that makes sense as we have a lot more water, a lot more moisture inside of our system now. So, if I were to peel up our aluminum foil just to take a look at the conditions inside of the beaker, everything looks clear. Despite there being some condensation on the walls, it looks pretty clear inside. Now the next thing we're going to do is light a match. We're going to let it burn for a little bit, and then we're going to toss it inside of our beaker. Seal it up for a little while, and look at that. You can see a little cloud funnel tornado thing starting to appear. Now, let's pop this open. Now you can see wisps of cloud coming right out. Now if we're to let this go for, a while, right, minutes on end, then this would still occur. All of this condensation, all of this cloud will still pour out of the beaker. Now in comparison, if we were to take another match, light it, let it burn, but then blow it out, there's smoke coming off of it. And in a few seconds, the smoke stops. So, one of the questions that we'll be asking in our lab is, what is it that's coming out of the beaker? Is it smoke? Is it condensation? Is it something else? And why? So, there we have it. that is going to be a walkthrough of the cloud in a beaker portion of the weather lab.
So that was the walkthrough. And I guess to touch a little bit on that very last portion where Darren, our lab manager, he showed the difference between where we have our cloud in the beaker, but all of that condensation, everything that's coming out, that will continue happening. All of the little wispy particles, that's going to keep on coming out, like after, and that happened after we added the match. But if we were to just light a match and then blow it out, the smoke from that match is going to go away. So after a couple of seconds, so that, and when we threw in the match inside the beaker, if we know that the smoke is, or like the fire and the match and all the smoke coming out of it is going to go away, then what did the match provide for the moisture to condense around to make our clouds? And that is going to be something you'll have to answer in that Lab 8 Canvas doc. So let me actually go back over to the Canvas page and go over those questions that you'll be answering. So this was our first page for our different weather parameters. The second page is referring to that video that we just watched on the lab experiment of making a cloud in a beaker. So for question 2, describe the conditions of your beaker after 1 drop of water evaporated and conditions stabilized. This was right after you added in those couple of drops of water, and then the beaker inside like stabilized after a couple of minutes. You don't have to answer question 3. So you can ignore question 3, where as you lower your fingers down the side of the beaker, explain how the temperature changes. So since you guys didn't actually do this, you don't have to answer this question. But basically as it changes is you have your beaker near the hot plate and the water at the bottom, it's going to be warmer. So as you lower your finger down the beaker, it's going to get warmer as you're getting closer to the hot plate. And as the temperature gets warmer, it's also clear, but in that warmer area, the volume of air there is, there's more space for your water to take up. So relative humidity near the bottom of your beaker is going to be low, but near the top of your beaker where it's cooler, there's less space for your water to take up, and that's why we see all the little condensation, and there's more relative humidity is higher at the top of your beaker. So you don't have to answer question 3, but that was that's like one of the relationships that we can see. For question 4, what is the point called where water starts to condense on the beaker wall? So on the beaker, as that line starts to change, as your level's condensation moves up, what is that line called? For question 5, describe what you observe when you look at the atmosphere inside the beaker before adding a burning match. So that was when we had the water, we added in our water, we closed our system, put in ice, but we didn't add the match in yet. What did it look like inside? And then for question 6, what did it look like after you added the match? Did any processes occur? What do you see then? For question 7, what did the burning match provide to the atmosphere of the beaker that produced the change you observed? So what did the match do to create that effect that we saw at the end? What did it give to our system to create our final cloud? And then for question 8 is going over the Excel graph with the double y-axis, and you're describing the relationship between air temperature and relative humidity. What do you see as air temperature as it gets warmer, as it gets lower, as it gets colder? How does that relate to relative humidity, and explain why this relationship occurs? So you can also talk about how humidity is dependent on temperature at this end. But that is basically what you have to answer and turn in for Lab 8. This isn't due until the next time we meet for Lab in 2 weeks. And let me share the PowerPoint again. So what you're going to upload is your responses to the Lab 8 datasheet, your Excel sheet with the Excel graph, double y-axis of temperature and humidity over time. Those are the two things. And again, note there's no lab next week because of the semester check-in. And so the next time we meet for lab is going to be on April 27th, that week of April 27th. Did anybody have any questions about the homework or anything like that? Okay. If not, I hope you have a good rest of your week. I hope you have a good next week off away from lab. If you have any questions, you can just email me. But if not, I hope you all have a good rest of your day.
Thanks, Maggie.
Thank you.
Thank you.
Thank you.
Sorry, just like quickly. My